Welcome to the TOEFL Listening section. In this section, you will listen to an academic lecture and then answer questions about what you heard. You may take notes while you listen. You will have time to review your notes before answering the questions. Listen to part of a lecture in a university class. You will hear the lecture only once, so listen carefully. After the lecture, you will answer some questions about what you heard. Some questions ask about the main ideas and supporting details. Other questions ask you to make inferences or connections between ideas. Answer each question based on what is stated or implied in the lecture.
Good morning. Today we will examine properties of light waves with a focus on wave-particle duality and the electromagnetic spectrum. I will connect classical wave descriptions to quantum particle concepts and show concrete examples that reveal both aspects of light. We begin with basic wave parameters. A light wave is described by its wavelength, frequency, and amplitude. Wavelength is the distance between successive peaks. Frequency is the number of peaks that pass a point each second. The speed of light in vacuum is the product of wavelength and frequency. When we discuss the electromagnetic spectrum, we mean the full range of frequencies, from radio waves through microwaves, infrared, visible light, ultraviolet, X-rays, and gamma rays. Visible light occupies a narrow band roughly from 400 to 700 nanometers. Each band has characteristic wavelength and frequency ranges, and therefore characteristic energies. Now I will connect the wave picture to the particle picture. In quantum terms, light consists of photons. Photon energy is proportional to frequency. This means that higher frequency corresponds to higher photon energy, because energy is proportional to frequency through Planck's constant. This relation explains why ultraviolet radiation can cause chemical changes while visible light often does not. Ultraviolet photons carry more energy per photon than visible photons. At the extreme end, X-rays and gamma rays have very high photon energies and can ionize atoms. The wave nature of light shows up in interference, diffraction, and polarization. The classic double-slit experiment produces an interference pattern that requires a wave description to explain fringe spacing and phase. Diffraction gratings separate wavelengths because different wavelengths interfere constructively at different angles. Dispersion is a property where the refractive index of a material depends on wavelength. A prism separates white light into a visible spectrum because shorter wavelengths are refracted more than longer ones in typical glass. This is the basis of spectroscopy, which we use to identify chemical composition from light. Polarization is another wave property. Polarized sunglasses block components of the electric field to reduce glare. Liquid crystal displays control the polarization state of transmitted light to form images. These are everyday applications that rely on the vector nature of the electromagnetic field. There are also practical considerations that combine wave and particle descriptions. In fiber optics, data pulses spread due to dispersion, because different spectral components travel at slightly different speeds in the fiber. At the same time, designers consider photon budgets, meaning the number of photons required for a given signal to overcome noise. Historically, the photoelectric effect illustrated particle aspects of light. When light of sufficient frequency strikes a metal surface, electrons are emitted. The threshold frequency depends on photon energy. This observation supported the quantized photon model and led to the use of Planck's constant in calculations. To summarize, properties of light waves include measurable wave parameters such as wavelength and frequency, and observable wave behaviors such as interference, diffraction, dispersion, and polarization. At the same time, photon energy links frequency to quantum particle behavior and explains many high-energy effects. In closing, remember the dual perspective when you analyze experiments. Use the wave description for interference and polarization, and use the particle description when you deal with energy exchange at the level of individual photons. That duality is central to understanding light.
Listen again to part of a lecture, then answer the question.
Higher frequency corresponds to higher photon energy because energy is proportional to frequency through Planck's constant.
This concludes the listening section. For more TOEFL practice tests and study materials, visit Spinta.org.